But wait, there are still more other graphical representations. Here we have time plot. We have an example, how does the depth of Echo Lake vary over time? We have historic measures, maybe season average of depth in feet over from 2000 to 2014. All right, so year is our X, depth is our Y. We plot them, and there's our time plot. And you can see there seems to be sort of a unfortunate downward trend. There's also some interesting sort of intermediate trends, a couple of years. There's a cycle, which is kind of interesting. But that's the time plot. There's not a whole lot more to that. The next thing that we're going to be doing is a stem leaf plot. Example is how much does it cost to make a Hollywood movie? So in one particular year, not necessarily current year, and I made these numbers up anyways, here are a number of movies that got made and how much it cost to make them. So for stem leaf plots, we create this kind of key. So what we're going to be doing is taking our first number generally and splitting it up in some way. And one part is the stem and one part is the leaf. And then we're going to take all of our numbers. I find it a lot easier to sort. That way it's in order because the stem leaf plot has to be ordered. And the stems, the smallest stem is 3 and the biggest is 16. If there's a stem which is not represented, notice that we have 7 to 12. There is no 8, 9, 10, but I still have those numbers here. That's important. You do have a continuous span of numbers. You take the first one and the leaf is 9. Right? The next one with 4, there are 2 of them. Well, leaf is going to be 4 and 8. And then you kind of keep going down the 5s, and then you end up doing all of them. It kind of looks like this. And really what this is doing is it's like a histogram on its side. But you can also get, your mean down here. I just got that for fun. Now the next stem leaf variation is the back-to-back stem leaf plot. This is if you have 2 data sets. I'm going to move Hollywood over to the right. I'm going to label it. There's Hollywood and Hollywood. Maybe there's a competitor to Hollywood. Over here, Nashville is trying to get into the movie business. And we collect a bunch of data from movies made in Nashville. We sorted it, and we can go through and make a stem leaf plot for Nashville. And it's going to be using the same stems, but it's going to be going, instead of off to the right, be going off to the left, labeling it Nashville. And that's what ends up being created for the stem leaf plots. There are those 3 5s and the 2 2s, 2 4s and 7s, right? And it's in order, right? That's actually kind of important so that you make sure not to miss anything. It's very easy, like if you don't sort this and you don't kind of do it in order, it's really easy to just drop something and miss something. And so you can see that even though the means are fairly similar, 8.7, 8.4, the shapes are really quite different. If you use a shape name here, this is pretty classic bimodal, right? Where this one is more of a mound shape, symmetric, right? And that all comes from the stem leaf plots. Now, next question is, how accurate is the manufacturing of the diameter of an engine crankshaft at a particular company? Right, we're still talking about stem leaf plots because there's a point of confusion. Now, when you're talking about sort of high precision engine crankshafts, really we're measuring out like extraordinary precision here, probably more than is reasonable. And we want to make sure that the manufacturing is relatively consistent, quality control. It looks like it's probably supposed to be 125 millimeters, but there's always variation in our manufacturing. I'm going to sort these, and I have my mean, which is pretty close to 125. Now, if I want to make a stem leaf plot, and if I use the decimal point to kind of divide my stem for my leaf, right, then my leaf is going to be, that 9. Now I'm going to go to the 8. The 8 is going to make the 9 round up, and it's going to be 125.0. Right? And so that's my key. And if I do that, everything rounds to 125.0, and it's a ridiculous stem leaf plot. It's of no use or no value. So you don't use the decimal point always for the division. That's the moral of this story. Well, where should the division be? Well, maybe we should divide 124.9, right, which means we would be rounding to that decimal place, which means this number, this 124.98811, would become this. And again, it's just not very helpful, right? So we move to the next level, see what that looks like. That's starting to get a little bit better. And it's not really until here that we start getting really enough spread, enough distribution to get a picture of what's going on here. And if 125 is our desired diameter, right, we can see most of the data is here. And now this will guide us in quality control. The question is, what's going on with those sides, so we can investigate what's going on with the manufacturing process. Why are we getting these somewhat extreme lows? And we just have to look into that. And so that's stem leaf plots. Now the last variation, well, it's not really a variation, it's a different thing. We're going to have a different example. How many shoes are sold each week at the local shoe store? And here we have our data. The nice thing about this is we just kind of look to see what's the max and min, and we create a scale that contains all of our data from min to max. And then we just go down one at a time. 25, and we put a dot. 40, and we put a dot. 30, and we put a dot. And we just kind of keep going down, putting dots. And as soon as you start doubling